Great. Welcome today. We'll get started. Happy Earth Day. I'm John Elliott, a Chief Sustainability Officer here at the lab. This event marks the first in a whole series of events this week. There's presentations, there's talks, there's displays, there's updates about sustainability activities, and even movies. So it's a lot of very interesting events this week. You can get a full schedule of the events if you Google Berkeley Lab Earth Week 2013. There's a full schedule of events and then also links to other events that are occurring this week. These events have been put together by many across the lab that are interested in advancing sustainability. I refer to us collectively as Sustainable Berkeley Lab. I would like to recognize one person in particular, Patrick Thorson in EHSS, who's been critical to pulling together the events of this week. A big spirit in doing that and also working through a lot of the details. So thanks for coming today. I will pass you now to Melissa Summers of Carbon Cycle 2.0 to introduce our speaker.
Thanks, John. Really looking forward to all of the events and for Earth Week this year. It's great that we're expanding LBNL's celebration of Earth Day to a whole week, unlike years past. So on behalf of Carbon Cycle 2.0, it's my pleasure to kick off Earth Week with a talk that we thought would set the stage for, sort of why care about the Earth and why we at Berkeley Lab are at the cutting edge of really understanding what's happening with our Earth system and the climate system. So today's speaker is Bill Collins, the department head for climate sciences and the Earth Sciences division at Berkeley Lab. Among his many acumens is the 2007 Nobel Peace Prize. He was one of the members of the Intergovernmental Panel on Climate Change, which won that prize along with Al Gore, and continues to contribute to that seminal piece of work that really underpins our understanding of climate change and its future impacts. He is developing a new kind of climate model that integrates cutting-edge climate science. Its goal is not to predict climate alone, but interactions among climate, water, energy on a global scale, and I'm sure we'll hear about that today. He trained in physics and astrophysics at Princeton University and the University of Chicago. And with that, I'm happy to turn the podium over to Bill.
Thanks, everyone, for coming today. This is on, correct? Good. So I wanted to talk today about the science that we are evaluating for both national and international assessments, and I'll come back to that assessment process in a moment. This really is a tale of two worlds, the one in which human civilization was founded 10,000 years ago, with the launch of agrarian agriculture, and has been largely stable since then, and the world that soon will be, which will be a dramatically different world, a world with an atmosphere that we haven't experienced since we had prehensile tails. So this is going to be two very different planets, and we're transitioning between the two, and I think it's a good idea for us with Earth Day to assess kind of where we are in that transformation process and what our prospects are for addressing that transformation. Along the way, I'll also talk a little bit about the science that we're pursuing locally to advance our ability both to predict the future and also, we hope, to figure out sensible mitigation strategies. But I thought, before getting all serious on you, I wanted to take you back 43 years to Earth Day 1970. This is partly just an excuse to enjoy the hairstyles of the period, but Earth Day 1970, this was a period, the hairstyles in particular in the lower middle graphic. I used to have hair that looked like that. That was Bill 1.0. Also the stamp, I wanted you to notice the stamp postage. This is before the launch of the stamps where the postage never expires because it keeps rising so rapidly. But the point of this picture was that back then, people were primarily concerned about the purity of the environment. They were worried about getting pollutants out of water, out of the air. They were worried about essentially water quality reducing soot, reducing sulfur pollution in the environment. Carbon as a major driver for Earth Day had not emerged. It was really, cleaning up the waste from industrial activity that was the original inspiration for Earth Day. And I'm happy that Earth Day has continued to grow and foster and is now moved into both worrying about these issues, which are quite critical but relatively short-lived, and also addressing the longer-lived issues associated with carbon dioxide. So I pitched this talk for a technical audience, and here we go. So my first graphs. How are we doing relative to Earth Day? Well, this is a graph of the concentration, parts per million by volume of CO2, starting from its pre-industrial concentrations at the year 1750 AD, where they were about 270, up to present day and then beyond, a projection beyond that point. In terms of just context setting, CO2 rose by 47 parts per million by volume in the 220 years between 1750, sort of roughly the advent of primitive steam engines, up to the first Earth Day. Since then, it's risen by an additional 68 parts per million. So the rate of increase, as this graph very much makes clear, has upticked in the 20th century. And you can also, if you now look at a blow-up of this, the so-called Keeling curve, this again is concentrations of carbon dioxide in parts per million by volume. You can see that this curve is convex upward. And we'll come back to how this relates to future projections. But at the moment, CO2 is increasing at a pretty rapid clip of about 3 parts per million by volume per year. So it's increasing steadily. We are at the point now in the science community where the issue of whether or not this is the cause of global warming is in the rearview mirror. I mean, I'm happy to take any questions you might have on that point, but as far as we can tell, and we've torture tested this hypothesis quite a few ways, this is the primary driver, along with a couple of other well-mixed greenhouse gases for climate change. And this is now regarded as very likely in the sense that it is more likely than 90 to 95% likely that anthropogenic greenhouse gases are the cause of recent warming. Again, if you'd like to talk about that or question it, I'd be happy to come back to that point. But this is the current operating hypothesis for the scientific community. And in order to look at the implications of that, we're in the middle of the 5th IPCC assessment. So IPCC stands for the Intergovernmental Panel on Climate Change. It's commissioned by the UN Environmental Program, along with a number of other international bodies. And there are 3 working groups. There's the first working group on the science, and I'm a member of that group along with Mike Weiner, who's in the Computational Research Division. There's a second working group that deals with the impacts of climate change on both society and the environment, and a number of people on campus are members of that working group. And then there's a third working group, which deals with efforts to mitigate climate change, and there are quite a few staff in EETD who've long been members and actually quite prominent leaders of that third working group. They're all staggered. They never meet in the same place at the same time. I don't know why, but we never met at the same time. We're always 8 time zones apart, kind of rotating around the planet. Our last meeting, just to kind of maximize our carbon footprint, was in Hobart, Australia. A very beautiful place. This is the harbor. Here's the 270 people who are working on the coordinating lead authors and lead authors in that chapter. We met in January of 2013. Here's my chapter group. So we break up into little groups, and there are about 15 of us who work in each chapter. Our chapter is dealing with how well do climate models work, and another very important question, which we can come back to in questions perhaps, why has global warming slowed recently? And is this a failure of climate models? And again, I'd be happy to talk about that. That's sort of the hot topic for our particular chapter. Why am I mentioning this to you? We sort of flew into the teeth of climate change, quite literally. So the setting of our working group meeting, it's Hobart, Australia. Australia had a very unusual summer. Now, as you know, January is summertime down there. They, after the fact, released a report called The Angry Summer by the government of Australia, 2012-2013, 123 records broken in 90 days, all over Australia. This is the fire risk for Australia, peaking in the southeastern corner. This was really severe fire danger. This is actually one of the fires setting up over Hobart. They closed most of the national parks just before we got there. A lot of people had gone in early to see things like the Tasmanian devil, which really is a real animal, not just a cartoon character. And they couldn't get out to the parks because the parks were closed. So it was incredibly intense. The day that we left and were flying, came through Sydney, it was 120 degrees Fahrenheit at the airport. There were fires on the tracks connecting the terminals. We eventually had to sort of dash up and take a taxi between the terminals. The air conditioning on the gangway into, well, the power systems on the gangways into the planes were crashing because they were trying to vent hot air from a power system into an even hotter atmosphere. And as you know, refrigeration doesn't work under those circumstances. And so it was just a crazy, crazy time down there. But Australia is not alone. The U.S. is getting warmer too. Last year was the hottest year on record for the United States. And there are a number of you in this room who have recently graduated from college who have never experienced a year with a temperature that represented our climatological norm here in the United States. So when I teach on campus now, no one in my class, unless they're a returning student, and I'm a student of life kind of like me in that age range, none of them have experienced a normal year in terms of temperature. So we are now in a different climate. Okay, this is not future tense. This is present tense. The climate is now different. A lot of you in this room who are early in your careers have never experienced a normal climate in the United States. Think about that. And by the way, I should say at this point, for the remainder of this talk, this is going to be kind of on the bracing side of the issue, right? So I'm going to present a series of challenges. I'm actually I'm a technical optimist, so I'm pretty sure we can solve this problem, but I think we have to face up to the reality first. And so this is going to be kind of on a little bit on I'm going to focus on the challenges that are facing us, and we can talk, I guess, during the question period about the solutions. Before I show you anything else, though, I am an optimist, even despite what I'm about to show you. So I'm now going to walk through some of the science that's emerged in the last 3 years. This is part of the science that we are assessing for the IPCC. There's also a national assessment underway. Mike Weiner in Computational Research Division is an important lead author on that report. So I'm going to show you the kind of the new stuff, but a lot of this new stuff is just going to be emphasizing science that we already thought we had nailed down. It's just getting tighter and tighter. This paper just appeared in Science recently, studied by Marcotte et al. This is an anomaly in temperatures. This is the difference in temperature relative to some sort of cosmological baseline for the last 10,000 years. Okay, just to remind you again, our estimates, and maybe my archaeology is old, but agrarian societies in the Middle East were launched at around this time relative to present day. So our entire human history, written human history, or at least sedentary human history, is contained in this record. And what this record shows, this is sort of like the extended version of the hockey stick, which now has been repeated by about 20 groups worldwide and is on very solid footing, is that you have this long period with maybe a curved handle and then a sharp uptick toward the end. We're in a period now where the global temperatures are the highest they've been in 4,000 years, since the time of Babylonian civilizations in the Middle East. As this graph makes acutely clear that there's been a sharp rise in temperature in the last, say, 400 to 500 years. If you blow this up and look at it even greater resolution, so these are temperature anomalies for the globe, from the northern hemisphere, from the southern hemisphere. So again, differences plotted in degrees Celsius relative to the climatological baseline. In this case, we've zoomed in to just roughly the last 120 years, so the end of the 19th century up to present day. And the main thing, obviously what you notice in all three cases is that the temperature is rising globally. It's rising in the northern hemisphere. It's rising in the southern hemisphere. I think it's useful to point out the southern hemisphere is dominated by ocean. So the idea that's been floated, unfortunately, was floated by Michael Crichton in his sort of very tendentious so-called science fiction book called State of Fear, is that this is all a heat island effect. We've studied that extensively. That's just bunk. Sorry to say. This shows up over the open ocean, temperature increase. It's very robust. What you find is that when you look over the northern hemisphere, where you have land surfaces, and they're leading the ocean in terms of global warming, in the recent past, the rate of increase has gone up to about a little bit more than 0.2 of a degree Celsius per decade increase. So there's been an acceleration in global warming. This is the rate over the entire record. It's just about 0.05 degrees Celsius per decade. It's jumped by a factor of 4 just in the last 30 years. And that's the reason why there's a separate set of lines plotted here where you see this steeper trend superimposed on the long-term centennial trend. As I mentioned, land temperatures are leading. This is another recent study from last year. This is work that was done by the Hadley Research Center, the same center of the email gate fame. And by the way, three different reports cleared them of any scientific malfeasance as part of that. So this is their latest analysis of temperatures. This, again, is a temperature anomaly. So warm temperatures are a net increase in temperature. Blue temperatures represent a decrease. And what you'll notice is that there are large regions over the contiguous United States, large portions of Eastern Europe and Russia, where there have been quite substantial increases in the temperature between 1960 and 1990. This is no surprise. The ocean has 100 times the heat capacity of the atmosphere, so it's going to take a lot longer to heat up, subjected to the same amount of energy input per unit area. And as we would have expected, and as the climate models accurately predicted, land is heating up substantially faster than the ocean. And this is one of the reasons why you see that big interhemispheric temperature gradient between the north and the south. You have land surfaces are equivalent to about 1 meter of seawater. The ocean itself is 4 kilometers thick. So that is the reason why there's such a large difference in heat capacities. Going along with this, we would expect from basic thermodynamics, due to the Clausius-Clapeyron relation, that as you heat the atmosphere, its capacity to hold moisture would also increase roughly exponentially with the temperature perturbation. And sure enough, the atmosphere is getting warmer. It's tracking what we would expect from basic thermodynamics. And it's getting more humid at the rate of about 1% per decade. So we're steadily increasing the amount of water in the Earth's atmosphere. That's going to have important consequences for storm activity. The combination of additional moisture plus some other physics that governs how the atmosphere works means that we are both shifting the bell curve of weather, but we're also fattening the tails. And the reasons why that's happening is that there's the amount of rainfall on the planet is governed by how quickly the atmosphere itself loses energy. And that's moving sort of linearly with time. Meanwhile, we're increasing the amount of moisture out at sort of creating a fat tail for really strong rainstorms. And as a result, we sort of expand the tails that lead to more intense storm activity. And this is sort of a particularly obscure index of that activity developed by a number of regional climatologists. But what they have found, and they looked at a combination both of droughts and particularly strong rainfall events, is that in relative terms, they were seeing 30% more severe storms over this period of time relative to a climatological baseline. So it appears to be a systematic uptick in strong storms, both over the United States, South America, portions of India, China, Europe, etc. And then there are places where we just don't have adequate data, for example, over much of Central Africa. But there are large regions where storm activity seems to be picking up. One of the challenges in assessing this kind of thing is that it's a needle in the haystack problem. So we're looking for very short-lived rainfall events, very short storms, cyclones, hurricanes, tornadoes, you name it. These events are small, highly localized. They just last briefly. And so we need tools to handle this big climate data. So I'm now going to do a segue into one of my infomercials for the lab. This is actually an infomercial for my colleagues in the Computational Research Division. This is a big data problem. And what we have done with funding from biological and environmental research, actually, is combine 3 tools to develop sort of the killer app for doing analysis of needle in the haystack problems in climate. We've combined a tool called Visit. This is a massively parallel analytical engine originally developed at Lawrence Livermore with an open source stats tool called R. along with another package developed at Livermore called the Climate Data Analysis Tool, to create a package where you literally can do analytics on very large volumes of data very quickly, and then perform statistical analyses on these to look whether or not the event is statistically significant, and then render that in a form that you can interpret it. And this is some recent work using this tool to look at storm tracks. The continental outlines are sort of faint here, but here's the United States, here's Asia. We did an analysis of storm tracks for storms simulated as they propagated across the Pacific, and we're now able to, in minutes, process problems, for example, looking at atmospheric rivers hitting the United States that would have taken 100 days or more using conventional methods. And what this analysis is showing us, just to summarize very quickly, is that if you take all the roughly 20 of the climate models that were used in the last IPCC assessment, they cluster into two groups. One cluster emulates the frequency of these atmospheric river events very accurately. That's the green dot here. And there's another cluster that tends to overpredict them. So we can already use this tool to sort of partition our climate models into models that are more realistic and less realistic for the purposes of assessing how these atmospheric rivers will impact California. And as you may remember, we had a very wet December thanks to one of these major storm systems hitting us during that time. Following on this theme of changes in the hydrological cycle, the other thing that's happening is a pattern that's known as the wet get wetter and the dry get drier. So there are parts of the planet which are, you can look at this in a variety of ways. One way of looking at it is, if you look over the oceans, is trends in salinity. So crudely speaking, places where the ocean has higher salinity, and this is a metric for salinity, it's basically parts per 1,000 of salt in the ocean water. Places where it's red are places where it's relatively salty, less rainfall. Places where it's blue have more rainfall falling on them. So not surprisingly, in the Western Pacific, where there's intense convection, lots of rain, it's a relatively fresh and very hot, actually, body of water, sort of a lens of very relatively salt-free, very hot water sitting in the upper ocean. A lot of rainfall in the storm tracks in the Northern Pacific, again, relatively fresh water. And then you find these large areas, particularly in the Atlantic and also in the Southern Pacific, where it has been relatively salty. And we can now measure the trends in the salinity using a variety of tools. And what you find is that the places, and here, red means it's getting saltier. Blue means it's getting fresher. So less salt content per unit volume of water. And what you find is that this pattern of reddening maps one-to-one with the places where it's already salty. So we're sort of essentially amplifying these patterns. I shouldn't say we, but climate change is amplifying these patterns in rainfall that have set up this pattern of dry getting drier and wet getting wetter. And this will have obviously consequences for water supplies. And I'll just anticipate the question in case it comes up now. We actually still don't know whether or not California is going to get more or less total precipitation by the end of the 21st century. The climate models just do not agree on this point. They do agree that we're going to get a lot less of snow. So the one thing we're sure of is that the phase of the precipitation is going to change. It's going to shift toward rain from snow. But whether or not we get more or less total rainfall is still an open question. About half the models say less, half say more. And so that's still certainly is going to be a challenge for water planners in the state. Continuing on, I'm going to march through a bunch of sort of climate factoids and then come to the projections part of this in a second. Sea level rise is accelerating, so we have a number of different estimates of that. This is a graph going back to the middle of the 19th century up to the present day. And this is sea level rise measured in millimeters. So for those of you who are relatively adept at doing metric, this is 250 millimeters, or roughly 10 inches worth of sea level rise, if you prefer to think in English units, since the start of this record. This early record was derived from tidal gauges. And since, more recently we have had instruments in space using GPS technology which can measure their distance relative to the geoid very accurately, and we're now using those, some of them, so both permanently active remote sensing to sense their distance from the ocean surface. So this recent record sort of blends over into the modern satellite altimeter record. And what's happened since 1993, sea level is rising at the rate of about 3 millimeters per year. So again, you do the math, multiply that by 100, and you get 300 millimeters, or about a third of a meter. That does not adequately account for the fact that a lot of this has been dominated by the fact that that water expands when you heat it slightly. I mean, it's a very stiff fluid, as you know, but the equation of state does allow for the system, the water will expand as you heat it. Much of this is known as steric sea level rise. About 3/4 of it is just the fact that ocean water expands when you heat it. 1/4 of it's due to contributions from frozen systems. So relic glaciers on land, and of course the major ice sheets. I should say that this number, and in fact, if you looked at the last IPCC report, it weighed in with an estimate that was around 30 millimeters, and that was 30 centimeters. Very controversial. That was one of the sources of one of the very few sort of open, I'd have to say, at least verbal fights that we had in the development of that report, because there were some people who said, this is a lowball estimate, you can't publish this. You're not accounting for all these other unknowns. And we just didn't know enough about the other unknowns to really push that number up. The new report is going to quote a number which I won't quote to you because I'm not supposed to, but it's appreciably higher by a multiplicative factor. So thanks to the contribution of the major land ice sheets, Greenland and Antarctica. So if you look at there's actually this graph both these graphs really represent some just amazing combinations of remote sensing. The one that I think is the coolest is probably the gravimetric measurements from space of the gravity of these, the local gravity perturbations from these ice sheets. So we can now measure, essentially infer their mass and the change in mass from orbit by looking at very subtle perturbations in the orbits of two satellites that are paired and tracking each other. And you can watch one of them sort of accelerate toward the surface as it passes over perturbations in the gravity field, and the second satellite following behind it can sense that, and then vice versa. So they can now measure the masses of these ice sheets in time. This is the mass loss for West Antarctica, which is a particularly vulnerable ice sheet, and it's been oscillating up and down around 0, but it's now trending negative. This is in gigatons of water per year, and a gigaton is a cubic kilometer of water. Greenland is right around in excess of somewhere between 200 and 300 cubic kilometers of water a year. So a cube of water, 6 kilometers on a side, length, breadth, and height. It's quite a large volume of water coming off that ice sheet. This has been inferred now both using the gravimetric method, and I wouldn't want to trust that if that was the only technique, but there's now laser altimetry that's also able to measure down to length scales, accuracies of centimeters, how high these ice sheets are, measure that relative to a baseline, infer from that how much the height is sunk, and then figure out how much the volume is decreased. So all these lines of evidence are sort of converging on these numbers. The other thing that's changed relative to the last report is our information about Antarctica. In the fourth assessment report, it was actually unclear whether or not Antarctica was gaining or losing mass. So the reason why it's losing mass, I suppose, is obvious. It could melt. Actually, a lot of the loss from these ice sheets is dynamic. I'll come back to this point in just a minute with my next infomercial. But about 2/3 of the ice loss from Greenland is dynamic. And if those of you can come back to see the movie Chasing Ice later in the week, and I understand there will be popcorn, so even more inducements to come back. If I had known, I would have made sure there was a snack truck outside here. But there will be popcorn, I hope, at Chasing Ice. But that's an incredible movie. Really emphasizes the dynamism of ice sheets. But the other thing that's happened to Antarctica is that it has an ozone hole over it. And the ozone hole has caused cooling of the atmosphere above Antarctica. Remember, I mentioned that the atmosphere around it is a lot moister. So you would vect in very moist atmosphere into a very cold atmosphere immediately above the continent itself, and of course you get more snowfall. So the center of Antarctica has been gaining mass, and in fact you can see evidence of that here. If you break this sheet up into east, which seems to be gaining mass slightly, and then the west, which seems to be losing, the net effect on Antarctica is that it's losing mass. Here's Greenland, and here's the total. This is now a cumulative mass loss since the start of these records. Roughly 4,000 cubic kilometers worth of ice have been lost from these ice sheets since the start of these records back in the mid-1990s. So this is contributing appreciably to sea level and will increase it way beyond the amounts that we would expect just from sea level expansion alone by the end of the century. To put these ice sheets in context, I mean, these things are not going to, we don't think they're going to totally go away, but in terms of the potential sea level rise they represent, Antarctica, well, let's start with Greenland. Greenland is 7 meters with the sea level rise. If it were to entirely go away, Antarctica is 70. So, you know, that would be a problem. And again, we don't think that's going to happen on any kind of rapid time, particularly rapid time scale, but it's going to be, there will be enough sea level rise this century to definitively impact the eastern seaboard in kind of a major way. Unfortunately, the simulations I've seen of this for Washington suggest that it'll just fill the tidal reflecting pool, but it actually won't get up to the steps of Washington, which is kind of unfortunate. You'd hope that the effect will be a little bit more immediate and attention grabbing, but apparently they'll just have a large, they won't be able to hold their lunchtime football games out in the park between them and the Lincoln Memorial during lunchtime. It'll be a lake. So during storms, severe storms. So what are we doing about this at the lab? As I mentioned to you, a lot of this ice loss is dynamic. Roughly 2/3 of the ice loss from Greenland we estimate is dynamic. And what that means is that we have to be able to predict the flow rates of the ice sheet all around this roughly 2 million square kilometer system. It's a big system, and we can't afford to, and unfortunately we have to treat we have to resolve the dynamics of this huge 2 million square kilometer system down to the length scale of individual fjords along its edge, so roughly one kilometer wide. That is not possible over centennial to millennial timescales using current computers. So what we've done, again, this is a partnership between my division and the Computational Research Division, is use techniques developed in the Computational Research Division, specifically an adaptive mesh technique called Chombo, to deploy our computing sources right along the perimeter of these ice sheets, where most of the velocities are highest. This color coding is the east-west velocity. This color coding is the north-south velocity. Deeper colors indicate higher velocities. So we just drop all the resolution and all the computing power on the edge where the action is, and we have functioning models for Greenland. We're actually one of the first groups to stand up functioning models now for Antarctica. This is 6 times bigger, so 12 million square kilometers, sort of the Mount Everest of computing land ice change problems, and we really have at this point, an internationally leading effort in being able to predict the dynamical evolution of Antarctica, thanks to this collaboration. So I think we will be issuing we hope to be developing some rather forward-leaning projections of sea level rise from these systems in the next year or two. Other places where these have been frozen for a long time and are sort of becoming unstuck, they're all changing fairly rapidly, and so you'll notice that a lot of these changes I'm talking about are in parts of the planet where when you go through a phase change, it's a big deal and it's really obvious, it's easy to detect. One of the other places that's experiencing a lot of change is the Arctic Basin. So the Arctic ice pack continues to shrink, and it's now, you can actually measure using microwave techniques whether or not you're looking at ice that was formed in the last year or whether or not it sort of survived one year and has hung around to the next. It's known as perennial and multi-year ice. Both of these are declining at the rate of somewhere in the range of roughly 15% aerial coverage per decade. And you know, if one were to extrapolate that out very far in time, well, you would find that you'd have essentially an ice-free Arctic basin during certain portions of the summer. The variability in the Arctic ice is also increasing. So this is just in a 5-year time span. the satellite records indicate that 42% of the ice disappeared from the Arctic and then it sort of recovered, but we're seeing these now very large, very pronounced swings in ice cover in the Arctic. This is a powerful positive feedback on the climate system because this ice reflects 90% of the sunlight incident on it, so it's like a sun shield in your car. When you replace that with open ocean has an albedo in the visible and the green of about 2%. So you go from 90 to 2%. It's as if you substituted the sun shield in your car for a black curtain. And as you know, that won't work. That's what's happening here in the Arctic. So this is an important positive feedback on the climate system. Okay, so that was my somewhat sobering tour through what's been happening. Let me turn now to the issue of what's coming up. So we in the climate community like to take the long view and sort of venture out into science fiction territory. So this is and of course when we do this we have to essentially make some guesses as to what direction humanity is going to go. Let me just check. My computer is saying one thing with regards to the time. Okay, good. Actually, these chronometers are all in sync. That's excellent. Yeah, I was sort of like, is that? I was looking at this relic timekeeping feature on the wall. I was worried that it was not tracking my iPhone, but they're all good. If you look far into the future, you have to account for what we, at least in the physical climate community, call exogenous data. By that I mean population growth. So we have to account for different population scenarios. We have to account for whether or not the people decide to choose a particularly green path, either because it's forced on them or because they get smart about how to use energy. And what we did for this latest assessment is we came up with several different, what we call representative concentration pathways. That's what RCP stands for, representative concentration pathways. These are CO2 concentrations in parts per million. I'll remind you that pre-industrial levels were actually below this axis. They started at 270. Here we are at present day, 2000. 2100 is right here. It's a third of the way across the graph. And then for a number of these scenarios, we projected that humanity would figure out how to stabilize CO2 concentrations at 2100 and then keep them flat. So we actually ran the models out for another 200 years just to see how the climate would respond. And in this case, this particular RCP, it takes humanity a really long time to wise up. This is essentially a no policy scenario. We are actually exceeding this curve at the moment. I hate to say it. So we're currently tracking this, but we're actually on the high side of it. So one can ask then, what are the consequences of following these different scenarios? And I won't. We deliberately, in the previous assessments, we had this very elaborate combination of socioeconomic scenarios with energy consumption leading to concentration pathways. This time around, we did something that I hope in retrospect will prove to be useful. We essentially said, here's the concentration pathway, and we'll figure out what different storylines on the humanity side might meet these pathways. This one, this pathway called RCP 2.6, which winds up not that far from Bill McKibben's 350.org target of 350 parts per million. This requires negative CO2 emissions by mid-century. So in other words, we have to be actively taking carbon dioxide out of the atmosphere by the year 2050 in order to hit this target. And the rest of these are done and envision that kind of very active carbon capture and sequestration. So, not surprisingly, this is a relationship, at least crudely speaking, that's been known since the late 19th century, the time of the scientist Arrhenius, who was the first person to sketch out, using paper and pencil, the relationship between CO2 and global mean temperature. So, not surprisingly, there's a one-to-one mapping between increased CO2 concentration and global mean temperature rise. The forcing, the perturbation to the greenhouse effect from CO2 scales logarithmically with this concentration. So the higher the concentration, the greater the augmentation to the Earth's greenhouse effect. And as a result, the planet has to, in order to sort of respond to that increased heat trapping, the planet warms up. And it turns out that the Stefan-Boltzmann law wins in the end, at least in our current climate, thankfully. And so that as you heat up, eventually you're able to ventilate enough heat back out to space so that the solar and infrared sides of the energy budget come back into equilibrium. But that, very crudely speaking, is the physics that connects increased CO2 concentrations with perturbations of the greenhouse effect to perturbations in temperature. And that's how these two graphs are related. We know this logarithmic relationship between CO2 and its perturbations to the greenhouse effect, thanks to physics traceable to Maxwell's equations, quantum mechanics and quantum electrodynamics, laboratory-grade spectroscopy. This has been shown repeatedly. It's just, although some people, I'm sorry to say, including in the physics community, love to come back and sort of like, I was at a meeting of the American Geophysical Union 2 years ago. I thought I was going to have to be physically separated from the person giving a poster next to me. He said that physics relationship is wrong. But in any case, this is very well-established physics. I'm happy to talk about that if you want to debate it. And it leads to this relationship. So what does this tell us? If you pursue a business as usual, well, essentially a no-policy scenario, you wind up with a temperature that's 8 degrees Celsius hotter globally than we currently have, starting from roughly present day. Now that doesn't, I mean, for those of you who, like me, have passed, either grew up or passed through Chicago on your way here, that, 8 degrees Celsius is kind of, it's kind of the warm-up to the temperature gradient between summer and winter. But it's actually a fairly big deal in a planetary sense. So this is the projected temperature increase for 2 time periods. And the one on the left, I'll come back to this in a minute. This is the temperature increase between now and in the next couple of decades, out to 2035. This is the temperature increase at the end of the century. And this temperature scale goes actually off scale here. 8 degrees and 9 degrees are up here. This goes in order from a scenario where we increase CO2, we actually decrease it by the end of the century, to one where it's on the order of about 900 parts per million. And you'll notice that the United States as a whole is heated by somewhere in the range of 5 to 6 degrees Celsius over its entirety. Russia, Canada are up in the range of 7 to 8 degrees Celsius. The Arctic is even hotter by the end of the century. This, again, is a very familiar piece of physics, this polar amplification. Oceans continue to lag the land. This is a radically different planet. This is, we have never experienced a planet this hot in human history. And by human history, I mean going back well into the Vostok ice core record. And this is a different planet entirely from anything that we've experienced going back to at least an ice age ago. I mean, if you go back 150,000 years, when the sun was doing this, the United States was hotter by, I think, around 6 degrees Celsius or something. I mean, this is an historically unprecedentedly different climate for us. And the challenge here, just in terms of thinking about this, now if we want to think about this in terms of real-world terms, how do we convince the public that this is a problem? Here's the issue. Imagine you're, a global leader, and I come in and tell you, you have a choice between either imposing a doubling gas tax prices, let's set them to European levels just for grins, right? Versus doing nothing. And this, by the way, is equal to, starting from now, 6 presidential election cycles. Okay, so who is going to step up to that challenge politically? Because the benefits don't accrue in this time period. 6 presidential election cycles out, virtually. It's kind of hard to see I mean, there's some difference over the United States, but not much. The benefits show up out here, and this is one of the reasons why climate change has proven to be one of many reasons why it's proven to be a particularly challenging problem in terms of messaging and communication, because it is the benefits of doing something accrue a ways out. This is not an air pollution problem. This is not like cleaning up the sulfur pollution from coal plants that immediately had a benefit for the acidification of lakes and rivers in the Northeast when they did this back in the 70s. This is a long-lived problem. CO2 has a characteristic lifetime in the Earth's atmosphere of 120 years. Precipitation continues to change. I won't go through this. So these pattern, the wet gets wetter, dry gets drier pattern just sort of magnifies with time, with implications for global water supplies. So the Sahelian, there are changes to rainfall all over, Africa, big changes potentially over portions of the Mediterranean. South Africa starts to see drought in places including the Amazon. We really don't want it because we're relying on the trees there to suck up the CO2, so that's an issue. And in the interest of time, there's some information here I'm going to skip quickly, just to sort of conclude the lecture and give time for questions. I wanted to get to a couple of ideas about solutions, just to, again, set the stage for why this is a tough problem, and then I wanted to leave time for questions. One of the challenges with mitigating climate change is that we've received a benefit from the Earth system, which is that roughly half of the carbon dioxide that mankind emits every year, and it's close to about 10 gigatons a year, half of that is stashed in living matter, plant matter, on land, and in plankton in the ocean. Okay, so that we get a benefit from nature. It's drawn down what would have been a really rapid increase in CO2 by a factor of 2. However, the piper must be paid, and if you were to suddenly drop your emissions, that carbon dioxide that the nature has stashed for you comes back out into the system. So this is some work that was done at Stanford by Ken Caldeira and his group, and you can ask, what happens if you let the CO2 concentration increase to this high level, and then you just dropped it. You managed to drop it to its pre-industrial level with a one-time CO2 removal. So you really worked hard for a period of a year, took out all that carbon dioxide. What would happen is that the carbon dioxide would then rebound on you because the carbon dioxide that's in the natural system that it's stashed for you comes back out, and this is that rebound. So we actually have to we have to draw down twice as much carbon dioxide in the Earth's atmosphere as is currently present in order to get back to the climate that we were in. So that's a factor of 2, unfortunately. So those benefits that nature has rendered us come at a price, and this is the price, that factor of 2. The other thing that's new in the 5th IPCC assessment is an assessment of geoengineering. This is an assessment that was published just recently. I won't go through these points in detail. It's essentially measuring how affordable these techniques are versus, these are in, as you can probably tell, dimensionless and highly qualitative units of affordability versus effectiveness. So, for example, one thing that would be, let's see, how does this go? So one thing that would be low effectiveness and low affordability down at this end of the scale. So one thing that would be sort of relatively cheap and highly effective, if you could keep it up for a long time, is to flood the stratosphere with aerosols, create your own volcano. Estimates are that this would cost perhaps a few $1 billion. You just fly 747s around at mid-latitudes where they can reach just barely graze the lower stratosphere, pump sulfate particles or sulfur dioxide particles out the back end of them, let them form aerosols, and very quickly flood the stratosphere, create your own volcano, and keep that up for millennia, no problem, right? So highly effective, highly affordable. And then there are there's some other things that get more exotic. Lower on the affordability scale, but also highly effective, is putting a solar reflector in one of the Lagrange points. As you know, we currently have a couple of solar satellites that are parked in one of the Lagrange points on the vector between the Earth and the Sun. They stare continuously at the Sun, produce fabulous information on solar dynamics. You could just park a big solar reflector there, made out of cheap reflective mylar, create sort of your own permanent sunspot at some cost. So this may be a logarithmic scale in terms of affordability. I'm not quite entirely sure. And then there's some other more exotic ideas on this graph. So this is not being assessed as part of IPCC. I was, as you could tell, being somewhat disparaging of this idea behind stratospheric aerosols. There's a model under comparison underway where people have allowed the climate to increase in carbon dioxide and then inject sulfur dioxide. This is the chemical precursor of sulfate aerosols to try to set the nest forcing to zero. And then imagine that, oops, you forget to do this, or some genius decides it's worked so well you just turn it off in the year 2070 because of budget cuts. And what happens is that climate change comes roaring back. So this is what would have happened to the Earth's temperature had you done nothing. Here's our nice, cool climate. Somebody says, well, we need this money for something else. Turn it off, and you realize the climate change that was present in the system in a matter of about a decade. In the meantime, of course, you've been acidifying the oceans like crazy. So it's not, this is, schemes like this, they represent a commitment that is unusual in human history's length. I mean, we're talking about committing ourselves to a mitigation strategy, unless we do something sensible about the carbon dioxide, that will require devotion to this for millennia. So just think about that for a few seconds. I think, it is, I have to end on, of course, the lab's own infomercial about this topic. So I think the theme here is that we're very sure about the science that connects CO2 to global warming to pretty serious consequences. And one can try a variety of Band-Aids. Those are now being technically assessed. The science is still developing, so I don't want to make any, it may turn out that there's some sort of magic arrow in the quiver, but by far the simplest thing is to stop emitting carbon dioxide. We're taking relic carbon dioxide that has been stashed for somewhere up to 400 million years and throwing it back into the Earth's atmosphere. And we're conducting a pretty large chemical experiment on the one planet that we know is habitable within, well, it's the only planet that we know currently is habitable. I guess Mars might be, we tried terraforming Mars, but that's definitely pretty speculative. So in the meantime, it behooves us to think about strategies for altering this. And so I think going forward, it's really incumbent on people like me who are doing climate modeling with colleagues in EETD who are doing energy analysis to partner with the rest of you who are working on a whole host of technologies to figure out, as we get ready to take these to scale, to truly industrial scale, what will be the benefits for the environment, what will be the co-benefits in terms of cheaper energy that's more sustainable with less environmental impact. And so we are certainly ready to partner with you on undertaking this challenge. But we don't have time to wait. So you have my email. Please contact me. Thank you. I'll be happy to take any questions you might have.
So it's just about 1 o'clock, so free hall pass for people who need to leave to get to the next meeting. But for those who want to stick around and ask Bill questions, we are webcasting this, so I just ask that you wait for the microphone to get to you so we can all hear your question. So go ahead and hands raised. See Jonathan.
I'm curious how you would respond to people who, if you think about policymakers and those who influence them, who sat through moments just like we are having here today in a lecture hall in 1970 and later learning about peak oil and about food crises and starvation, and they look at today and say, oh, it didn't really turn out so bad. How would you explain to them the difference in the quality of information that you have today compared to the information that was the basis of those projections 10, 20, 30, 40, 45 years ago to try to get across to them that this is different?
Well, I can't, obviously peak oil has been one of those things that's been around oil has been peaking for a long time. And that seems to have a very flat and very shallow curve. No, the predictions about this, and actually there's a fascinating book by Ray Pierre Humbert called The Warming Papers, where he traces the history of global warming back to Arrhenius in the late 19th century, and then what happened to that literature. There was actually fairly active research in this up until the 20s, and then it just stopped for almost a 40-year time period, came back at the Geophysical Fluid Dynamics Laboratory and elsewhere, well, actually at Scripps and at GFDL in the late 50s, early 60s. What I would say to them is well, okay, so maybe there are two questions embedded in it. One of them is the climate changing? I think even the skeptical community has gotten past the point where they're challenging this data. I mean, as you know, people like Richard Muller did his best analysis and did his best job at trying to shoot this stuff down, and came out converting from a skeptic to believer, and now even believes that anthropogenic causes are the cause of global warming. Right? So the evidence is pretty good. I guess the other thing one could question is, are the models sufficient? We now have a chance, looking back over the last four assessments of IPCC, to look at how our predictions from the late 80s and early 90s have tracked reality. And they're tracking reality to within about 50%. So there are uncertainties in how these models are, there are uncertainties in the boundary conditions that we can't control for. So this may not be a model issue per se. It may just be our lack of knowledge about how much sulfate pollution we're emitting to the Earth's atmosphere. But the models are tracking, model predictions that we made 25 years ago are tracking what's happening now. So we now have evidence. You don't have to believe me. You don't have to trust me when I tell you that these models are really carefully formulated. We have solid evidence that you can go back and unearth that the models have been doing a decent job for the last 25 years. Even more importantly, and predicting global mean surface temperature is one kind of prediction. They've predicted much more interesting signals in the climate system that were theoretically predicted before the models predicted them, or at least had not been. They were certainly, the models made predictions before these phenomena were observed. For example, warming of the lower troposphere, cooling of the stratosphere, some other subtle temperature gradients involving the coupling between the Hadley cell and the Ferrel cell at higher latitudes. The models are doing a good job. And, what do I say to them? Okay, fine, you're skeptical. Well, what's the basis of your skepticism? They don't, I'm sorry, but the shoe is now on the other foot. Right? We're past the point, I think, where the climate community has to prove the case. We continue to have to prove it, but the burden of proof now rests with the skeptics. They may not have realized it, but it's certainly the case. There's a question over, yeah, two questions.
I was wondering about the afforestation solution. That seemed to be a pretty economical and good solution. What are some of the policies that we would need to do, and what are some of the limitations of that solution?
Not enough land surface area, for starters, right? I mean, we're talking about that would require a very large increase in. The higher you go, right? I mean, we're talking about once you get to. To give you for instance, let's see. Suppose we were to follow one of these scenarios and more or less increase carbon dioxide by a factor of 2.5, just as a for instance, right? That's the business. That's the policy as usual issue right now. The amount of carbon that you have to remove from the atmosphere is equal to the entire amount of carbon stored in the terrestrial land surface system, including soils and forests, right? So we're talking about situations where you just can't plant enough stuff to act as the sink. The ocean, of course, ocean is 50 times the Earth's atmosphere as a reservoir, so you can wait for the ocean to act as the great sponge, but that, unfortunately, has the characteristic turnover time of the ocean, which is millennia. So afforestation is a very useful strategy, don't get me wrong, but there will come a point beyond which it simply will not be able to work. And certainly the business as usual scenario essentially requires you to remove as much as all of the land surface, soils, plants, everything, all carbon on land, including the microbes in the soil, which is most of the biomass on the planet, all of that combined. I just don't think it's feasible. Yeah.
Yeah, thank you, Bill. I have a question sort of related about the geoengineering graph you showed, and I'm glad to see you're looking at these comparisons, and it appeared as though carbon capture and storage, which first of all I wondered if it was being considered geoengineering, and
It
I think
is,
it was.
yeah.
Yes, and it appeared to be in the center of your graph. Is that by definition?
I would have to go back and look at how. I mean, to be honest with you, I'd have to go back and look at how this
Okay.
how these metrics were derived in
yeah.
greater detail. So I was primarily trying to illustrate the multitude of strategies that are under evaluation. There's a and as I mentioned this time around in the first working group report, there's now some explicit consideration of geoengineering strategies, based primarily on what climate models and the historical climate records say about them. So, for example, flooding the stratosphere with aerosols looks a lot like the Pinatubo eruption. So what did Pinatubo tell us about how the hydrological cycle would respond? And then experiments like the one I just showed you from this geoengineering modeling and comparison project. Yeah.
So a quick second question, maybe quick, is methane. So given if we have happening right now fuel switching from coal to natural gas, are people looking at the effects of
Yes.
burning that methane or residual methane emissions itself as a greenhouse gas?
Yeah, there are a number of studies looking at primarily. The concern there is primarily with leakage. On sort of the relevant time scales of a few decades, methane has an effect that's roughly 30 times increases the greenhouse effect 30 times more than a molecule of CO2 on a particular time horizon, which is measured in decades. That means that you can tolerate a very small amount of leakage from the system before any benefit that you gain from the improved efficiency of engines burning natural gas is offset by the leakage. Right? So just a few percent leakage would entirely cancel out the effect of the benefit of the higher thermodynamic efficiency of engines burning natural gas. And Cornell has done a study on this. So managing leakage is a big deal. Currently, this whole thing is framed around energy security, unfortunately, not really, not around the benefits for CO2. And I will say the one thing that's I think a little bit of a challenge is that Europe is having a terrible time with their carbon market, right? So they like, as you know, California has its own has a carbon permitting system. Europe has one as well. It's they did two things have happened recently. First, the price of those credits is now hit rock bottom, and the second thing that happened is that they set their cap too big. So there was actually some evidence that there was a little bit of people creating some wiggle room for themselves. So they set a very big cap with the understanding that they would shrink the cap, and obviously that's how cap and trade eventually gets you down to eventually everybody's sort of scrambling for that last few carbon credits. They just recently tried to shrink that overly large cap that they have, and the measure failed. So anyway, we need to be careful what solutions we pursue in the teeth of the fact that carbon controls are struggling both, certainly in Europe, where I thought they might be showing the rest of the world how to pursue this. Not yet. There's a question in the back. Yeah. I'm an optimist because we get 6,000 times as much sun over the Earth's surface as we need every day for all humankind combined. Right? So we just need a fraction of a percent of that of the land surface area, and then highly efficient solar cells, which we currently have, to meet mankind's energy needs. Storage is not addressed by this, of course, but in terms of knowing that we have a renewable energy source, either sunlight or sunlight converted into gravitational potential energy in the form of water behind dams, or converted into kinetic energy in the form of wind. We have ample sources of energy here. And we have more than enough nuclear fuel on planet, conventional fissionable fuel, to power reactors for centuries to millennia. So between solar energy and nuclear potential energy, we have plenty of energy. However, so that's the reason why I'm an optimist. There are no fundamental physical or chemical barriers in the way of moving to sustainable energy. That's of course, a scientist's perspective on just how easy economic and political issues are, but I'll grant you that. But I would not be an optimist if there was a fundamental physical law in our way, but there's not. So I'm an optimist. Physics to the rescue. Other questions? If not, make sure you come back for the events for the rest of this week, and there will also be an event this evening, Berkeley Lab event at Science at the Theater. So thank you very much, and celebrate Earth Day.
Thank you, Bill.